Hello. Today we're going to be talking about the optimization problem where we have a right circular cylinder inscribed inside of a cone with a height of x, h, and a radius of r. Now what we can see here is we have that figure drawn right here, where we have a cone with a height of h, a radius of the cone is r. We have the height of the cylinder is going to be h minus y, and the radius of this cylinder is going to be x. Now, the formula for the volume of a cylinder is equal to pi times the radius squared, which is x in this case, so that's x squared, times the height of this cylinder, which is going to be h minus y. Now, we want to optimize this equation, but it's in terms of two variables. So we use the idea of similar triangles to write the volume equation in terms of one variable. We know that the height of the major triangle, which is this part here, is going to be a height of h and a radius of r. And we know that we have another triangle, which would be the top of the cylinder, which has a radius of x and a height of y. Now, by similar triangles, the ratio of the triangle legs are equivalent. So that is to say, y over x is equal to h over r. Now, we can use this here, this equation, to solve for y so that we get y in terms of x. So multiplying both sides by x, multiplying both sides by x, we get y equals hx over r. So what this is saying is y equals hx over r. And we can input that into, or substitute it back into my volume equation so that everything's in terms of x. So my new volume equation is going to be pi x squared times h minus hx over r. Since I plan on taking the derivative of this, I'm going to keep going. So this is going to, I'm going to distribute. This is pi hx squared minus, this is going to be pi hx cubed all over r. And so this is the volume equation that I'm going to use to optimize this optimize the volume of the cylinder inscribed inside of a cone. So the next thing that I want to do is I want to take the derivative of the volume. So the derivative of the volume, v prime, is going to be, so we have two constants, pi and h. The derivative of x squared is 2x minus, now the pi h over r is a constant, so that's going to be in front of the derivative. And the derivative of x cubed is 3x squared. Now that I have the derivative, I want to set this equal to 0. So I'm going to rewrite this and set this equal to 0. I'm going to do a little moving around as I rewrite this. So this is going to be 2 pi hx minus, this is going to be 3h pi over r times x squared. And this is going to be set equal to 0. Now, I look at this equation and I have two terms. And in both of these terms, I see that an h and a pi are common. So I'm going to and an x. So I'm going to factor out a pi, h, and an x. And I'm left with 2x, or sorry, just 2, minus 3x over r. So 3x over r. And this is all equal to 0. Okay, so now I have two factors here. One solution is x equals 0. The other solution is from the equation 2 minus 2x over r equals, 3x over r equals 0. Now, we are trying to solve for x here. And x represents the radius of the cylinder. That represents this radius here. So this radius has to be a number of some kind. It's got to be larger than 0. So x equals 0 is not possible. So we want to solve this equation and see what we get. So I'm going to subtract 2 from both sides, and I get negative 3x over r equals negative 2. And so then continuing on with this algebra, I'm going to multiply both sides by r over negative 3. And I get x equals, this is going to be 2r over 3. And so the radius of this cylinder needs to be x equals 2r over 3. Now, what does y have to be? So what does y have to be? Well, y, we know, equals hx over r. Okay? And we know x has to be 2r over 3, so let's put that in. So that's going to be h times 2r over 3 all over r. And so then I'm going to clean this up. So that's going to be 2hr over 3r, which then becomes 2h over 3. And so this is my y value. Okay. Now, we want to know what is the maximum volume for the cone, the cylinder, inscribed by the cone. So the volume max, or the max volume, so volume max, is going to be equal to, we have pi, x is equal to 2r over 3, and we square it, times, we have h minus y in the original case, and we know y is, so h minus 2h over 3. And we can clean this up. So the first one, we have pi times 4r squared over 9 times h over 3, because we have h minus 2/3 h. And so then this becomes, so we have 4, a pi, an r squared, and an h. So 4 pi r squared h all over 27. So what this says is, you tell me the height of any cone that you're inscribing this cylinder inside, and you tell me what the radius of it is for this cylinder inscribed inside the cone. This right here would give me the maximum volume I can keep a cone inside it.